Okay, today we are going to talk about chapter 6, which is dealing with introduction to convection. So far we have been treating convection as a single value. I was giving you h value for many types of problems, exam questions, homeworks, so on and so forth. H was given to you and we didn't need to do any calculation to find what h is. So from now on we will go further into details of how to calculate h and what are the parameters that controls h. So these are the types of the discussions that we are going to have today. Okay, so to be able to understand the significance of h, we need to understand the boundary layers. So velocity boundary layer, heat boundary layer or thermal boundary layer, and mass transfer. So these will be our main focus on chapter 6. So let's start to talk about velocity boundary layer. So let's take a look at this figure here. Let's imagine that we have a fluid. Let's say it has a bulk velocity u infinity. For the sake of simplicity, let's call this velocity, let's assume this is 100 meter per second, okay? So this is the velocity of the bulk stream. And if we send this fluid over a plate, as shown in here, so we know from fluid dynamics that the fluid molecules that are just above the plate are going to stick to that. So that means there will be no slip boundary condition. No slip boundary condition. So that means the velocity at the base of the plate, velocity of the fluid at the base of the plate will be 0. And if you go infinitely away from the plate, the velocity will be bulk velocity because the fluid is not going to feel the surface boundary condition. So that means it's going to flow in an unperturbed manner. So the velocity far away from the plate will be 100. So obviously velocity will change from 0 to 100, but this change happens in a particular way, and this change happens in a very rapid fashion within a thin layer. So it changes from 0 to 99 within a very thin section of the fluid, and that thin section is called a velocity boundary layer. And then change from 99 to 100 happens in a very, very long distance. So it's basically, it's a fairly long distance. So in general, this is the region that we care about the most because most of the changes, energy transfer processes happens in this region. And this is the velocity boundary layer. Formally defining, if you like to define velocity boundary layer, so it is defined as thickness of the velocity boundary layer is defined as the distance from the solid body to the point at which the viscous velocity is 99% of the free stream velocity. So if this is 100, this line indicates velocity of 99. Okay, so that is the velocity boundary layer. And similarly, so in addition, if you like to define this region, so within the velocity boundary layer, we'll be using symbol delta to indicate the boundary layer, that this is the thickness of the boundary layer changes as you go away from the leading edge. This is the leading edge. As you go further down from the leading edge, the thickness of the boundary layer changes. But in all cases, so if you follow this black line, so it is always 99% of the bulk velocity. So that is the definition of boundary layer. So if you need to calculate the shear stress at the wall, tau is shear stress. Okay, so it is force per unit area. So shear stress is defined as viscosity times the velocity gradient. So velocity gradient, this is the y direction, this is the x direction. So the velocity gradient, which is evaluated at the wall. Okay, so this is the shear stress. And if you want to calculate the drag force, the total drag force, basically you integrate all of the shear stresses across the surface area. So if you think about, this is the top view, so we integrate all of the shear stresses at the wall, and then the sum of the shear stresses gives us the drag force. If you have a constant shear stress multiplied by total area will give us the total force. Okay. So let's talk about thermal boundary layer. And in this case, so we are interested in temperature rather than velocity. So let's say we have a fluid which is at 100 degrees Celsius. Okay, this fluid is at 100 degrees Celsius. And let's say we have a plate which is at 0 degrees Celsius. So what's going to happen at the plate? The velocity, the temperature of the fluid will be 0 because it is in contact with the plate, and the temperature has to be the same. So you'll have 0 degrees Celsius at the fluid molecules right above the plate. And if you go very, very far away, the temperature will be 100 degrees Celsius, and the temperature at the plate is 0 degrees Celsius. So as in the case of the velocity boundary layer, the temperature will change very rapidly within a thin section of the fluid. And in here, the temperature will change from 0 to 99 degrees Celsius. And this region is called thermal boundary layer. So the thermal boundary layer is the region the temperature changes 99% within this thin section of the fluid. Okay, so in here, so we want to just pay attention to the direction here. So if you think about it, velocity, so if you may also have the opposite situation. You may have a cold fluid, and then you may have versus 100 degrees Celsius plate. So you may be using a cold fluid, hot plate, or hot fluid versus cold plate. So different possibilities are possible. So you basically need to, the direction of this gradient will change depending on if the fluid is hot or if the fluid is cold with respect to the plate. So the direction of this temperature profile may change depending on what is the hot place, what is the cold place. Okay, so, and the definition in terms of finding the thickness is very similar to the velocity profile. So if you want to calculate the flux, the heat flux at the surface from wall to the fluid, so we are using this equation. This is the thermal conductivity of the fluid. Okay, so right now we are interested in convection. Convection means that we are dealing with a fluid. Whenever you are doing a convection calculation to estimate H, you will be concerned with the fluid properties, and this is the thermal conductivity of the fluid. So that means the heat flux at the slightly above the plate is dt by dy, which is evaluated at y equal to 0, and multiplied by the thermal conductivity of the fluid. And we define local or convection heat transfer coefficient as the ratio of Qs double prime divided by delta T. So delta T here is Ts minus T infinity. This is delta T, and this is our heat transfer heat flux at the wall. So the ratio of the heat flux to delta D is the official definition for H. Okay? So similar to velocity and temperature boundary layer, you may also have a concentration boundary layer. In this case, the variable is concentration. So you can imagine, let's say we have pure water which has 0 gram per liter salt. And let's say you have a salt block which has 100 gram per liter concentration. And as you can imagine, when you flow this pure water over the salt, there will be solubilization, there will be a gradient in salt concentration, and the concentration will change from 0 to 1, and eventually it will reach to, so from 100 to 1, and eventually reach to, so 99% of the change in concentration happens in this region, and this is called concentration boundary region. So in terms of the equations, so we have mass flux, which is diffusivity times the concentration gradient evaluated at the wall. And again, this is diffusivity of species AB here. So you can also define a convective concentration gradient as the ratio of Na double prime over delta C, delta concentration. So you'll be dealing with this in mass transfer class. I know some of you are taking this class in parallel. So again, I'm not going to go too much into details, but I'm just going to highlight the similarities between mass transfer and heat transfer. So now let's talk about significance of boundary layers. So the idea is simple. As long as you have a flow of fluid above a solid object, there will be a velocity boundary layer. So as long as there is a flow and there is a solid surface, if there is a solid surface and if there is a fluid flowing above it, you will have a velocity boundary layer, and that's also going to have a surface friction as long as mu is not equal to 0. So as long as mu is greater than 0, you will have this. So likewise, as long as you have a solid object and a fluid which is at a different temperature flowing above this, then you'll have thermal boundary layer. So you need to have two key points here. One is the temperature difference between the fluid and the object, and the second is the existence of the fluid motion. So the fluid has to move, and fluid has to be a different temperature. And if these two are satisfied, then there exists a thermal boundary layer here. So likewise, in concentration boundary layer, you have an object, you have a fluid. So the fluid is going to flow around this object, and as long as there is a concentration difference between the fluid and the object, and as long as you have a fluid flow, then you have a concentration boundary layer.